All right, everybody, 4 o'clock. Welcome back to your favorite class. Yes. All right. Right. Homework 1 was due to my mailbox literally 10 seconds ago, so I hope that you got that in. If not, oh, too bad. Okay. I've posted one more assignment, and that is something I talked about at the very first lecture, and that is the manufacturing breadth assignment. So we're starting in on composite manufacturing. We're going to end it today. And I don't have time to really go into the depth that I really want to, so I'm kind of forcing you guys to maybe take some effort here and write for me a paper on composite manufacturing. All right, so a lot of the information that you'll go into this particular writing assignment you can just take directly from the notes. So I'm asking you to do things like, I'll just pull up the assignment so that we can all see it. It's maybe easier that way. Okay. Come on, you can do it. Come on. There we go. All right. So here's your assignment. I posted this on Blackboard. It's going to be due Thursday, October 8th. That's 3 weeks from today, so quite some time. And this year, just basically going to provide an overview of 5 different manufacturing topics, and it's kind of the topics that we're talking in class. We sort of made our way last time through these 3 guys, and we're going to talk about these guys for the remainder of class today, and we'll start in on new material after that. So these 5 methods, just kind of ask you to overview them, maybe 1 page per. Talk about things like very brief description of the process, some typical materials that you might see manufactured with these particular methods, modern objects commonly made, and benefits and drawbacks. So most of this material you can probably just take directly from my notes. You might need some additional references to the outside, like I found from this website that they make hockey sticks using this particular method. All right, that would be cool information. All right. So 12-point font, typical line spacing, no longer than 5 pages. You should be able to get it all in there in 5 pages. Okay. I don't think it's all that difficult. You could probably get started on it right after the lecture today. So I'm giving you plenty of time to do this. Please make it happen. Don't wait till the last minute, like I know you were apt to do. Right. So let's get back into it. We'll get back into the composite manufacturing, and I actually brought some samples today as well. So maybe we can start by a little review here quickly, and then we will pause once I get to the point where my samples are relevant. All right. So we were doing composite manufacturing last time, and we sort of just dove right in. Is this showing up on your guys? Yeah, annoying. All right, get out of here. How do I get that out? Go away. All right, be gone. So we talked about the things that are influential in manufacturing composites, mainly pressure and temperature. And we talked about the 2 different types of processes, dry and wet processes. A dry process would be a process where you place the fabric sort of in dry form into the mold. And a wet process would be you get the fabric wet with resin before you apply it into the mold or on the mold surface or whatever the case may be. So here are some examples, and we talked about the processing materials. And this is where my sort of example comes in. I have here a composite that I have manufactured. All right, this here I'm going to try to show it in the camera for the people on Microsoft Teams. Welcome, by the way, those of you online. This is a carbon fiber sort of plate that I manufactured here at MSOE. And this particular guy has got, let me make sure I got this right, 6 layers of unidirectional carbon fiber. Right, so remember we talked about sort of the fabric being unidirectional, all sort of in one layer. So I've done that here. I've stacked the carbon fiber 6 layers on top of each other, and then I put this on an aluminum plate, put it in an oven, put some pressure on it, and let it cook for about 2 hours. All right. How much money did it cost to make that? Me? Nothing. The university paid for it. Okay. How much money did it actually cost to make this? This guy here, materials, I don't know, 50 bucks. Cost of manufacture, another 20. So this costs probably about 70 bucks to make, something like that, if I had to guess. But I'll pass this around to the class, but I'll just emphasize the fact that it's like very strong, very stiff material. All right. So on par with what you might think of like steel or aluminum. Now, I brought this here not because of the sample itself, but the sample is cool in of itself. But I also wanted to bring the additional materials that I used to manufacture the sample so that you can sort of see what I mean physically when I talk about some of these materials that go into it. All right. So obviously this is the carbon fiber itself. But there are a variety of materials that I needed to use during the manufacturing process to make this thing happen. All right. The first being the aluminum plate upon which this thing was laying. All right. So here's an aluminum plate, and I laid this down on top of that aluminum plate. Now, one thing I talked about last time is that in order to be able to remove this particular piece off of the aluminum plate after the manufacture, you have to have what's called the release film. All right, it's a non-porous film, and that's what's actually on this side here. So we can probably see this on the camera. It's a very thin, like nylon film, basically. It's not nylon. It's actually ETFE. Is the actual polymer here. These blue pieces here are tape that's meant to hold the film down. Okay. So we see the aluminum, we see the thin sort of pink looking release film. And so this is sort of how this thing was built up. You have this aluminum plate, this pink release film, and then I placed all of this was originally wet fabric onto this release film, just like this. All right. On top of that, we have to have like another release layer, but that release layer needs to be porous because if there's extra like liquid resin that's in there, we want to sort of squeeze that out. And so we place that porous film over the top of that, and then we place our bleeder cloth on top of that to absorb the extra resin. And I peeled both of these together off of the composite after the manufacture, and that's what you see here. So those of you on Microsoft Teams, this green layer here, this is the porous release film that was on top of the structure, right? When it came off of the thing, and then this white cloth here is kind of like a thick tissue over the top of that. So the entire assembly here would be this cloth, this nylon release that's porous, all over the top of what would be, oh god, that fell out. This is hard to do. What would be inside there, the composite material. Then there's an aluminum plate that goes over the top of this. You come press it like a sandwich, and away you go. All right. So I'm going to pass all these things around to the class. You guys just get a feel for it. Um, I'll give it to you in the way that it was actually assembled, and then you can see. You'll notice in the bleeder cloth there that there's some like amber-colored epoxy that has kind of come through the process. So you can see the bleeder cloth and its usefulness there in absorbing the extra like epoxy that came through during the manufacturing process. All right, so that's kind of what I'm showing here with these processing materials. All right, we talked about a variety of different dry processing. Resin transfer molding was one. We talked about the fluid flow, how that's an issue, the general production throughput for RTM. Vacuum-assisted resin transfer molding. This is pulling the resin through, wetting the fabric. Showed some examples here. Useful for making windmill turbine blades. Here's an example of a windmill turbine blade in production with Fardum. Reaction injection molding, mixing part A and part B quickly, injecting into a closed mold that has some fabric laying in there. Usually the cure time here on orders of minutes, and this is for high production thin materials. Then we get into wet processing. Did Dr. Hart get quieter for anyone else? Oh, am I quieter now? Rawr! I'll get louder. All right. I'll try to bring the mic maybe a little bit closer. I try to get it close because the mask makes me muffled a little bit. So I'll try. So anyway, we also talked about wet fabric, specifically prepreg. Prepreg is basically this carbon fiber or your reinforcement material that has already been impregnated with the resin and then frozen for use at a later time. How we make prepreg, these are the couple techniques we talked about. Solvent impregnation and hot melt processing. Then I played for you the German techno music that showed the tape laying of the carbon fiber on the mold using sort of this wet prepreg. Again, talking about another wet processing technique, which is vacuum bagging, where we sort of put vacuum bag over the whole thing and apply vacuum to suck out extra resin. Here is an example, a couple pictures of that happening. A happy customer with a wing element at the end. And then autoclave processing. Autoclave processing is putting all of this assembly into a positive pressure environment, like a big pressure cooker, and providing positive pressure to the layup that you might make. So here's a cross-section of the composite. We see a vacuum line here that might provide negative pressure inside of your vacuum bag structure. And also we have pressurized air that might come into this autoclave to sort of provide that positive pressure that you need, all while the autoclave has the ability to heat up to really high temperatures. So pretty impressive like piece of equipment. And here was a plate that looks very similar to that plate that I just passed around coming out of the autoclave. All right, this is about where we left off last time. Autoclave advantages and disadvantages. So when we were talking about autoclaving, we said that the advantage here was because it's got this big pressure cooker, you can more or less give the highest fiber volume fractions possible. And we'll talk about this a little bit later when we talk about the mechanics portion. But the more fibers that you can pack into your composite, the more load carrying capability that composite's going to have, and the better it will be. The more pressure that you can provide during your manufacturing process, you can just put that up here, Matt, thanks. The more pressure you can provide during the manufacturing process, the better fiber volume fraction you're going to get. So generally, the more pressure that you can apply, a higher fiber volume fraction, the stronger, the stiffer the material. So that's good things. All right. Therefore, the autoclave is like the best manufacturing method. However, it is by far the most expensive manufacturing method. All right. It can also be very time consuming because you have to like pressurize this big pressure cooker, which takes some time. You have to monitor the process, usually with an autoclave operator during the entire process. Some of these cure cycles can be, 24 hours. So you got like multiple operators that might have to monitor this process. So those are the big disadvantages of autoclaving. Kind of cool couple pictures here I wanted to show. Top right here, this is a mold for the 787 fuselage. This is one portion of the fuselage. So you see here this like mold that they've created. And I don't have a great scale on this, but I mean, you guys know about how big a fuselage is. So this is maybe 25 feet in diameter around, right? So this is a huge mold that they're using to lay carbon fiber upon. And then they have to take this huge freaking mold, which is 25 feet in diameter, and put it in an autoclave. Like, oh my goodness. So you have to make an autoclave that's like, I don't know, 30 feet in diameter, maybe bigger, that's, 50 feet long. Yeah, I mean, you got to pressurize that whole thing with nitrogen, and it's like a big bomb you got in your like, processing facility. Oh my gosh. Like, I just like pressed the button as the autoclave operator, just like, hunker down. Just hope nothing breaks. So here's the mold inside of this autoclave. So you see this yellow sort of perimeter here? This is like just a pressure vessel. It's a giant pressure vessel. So they're going to eventually close the door on that pressure vessel and seal it up and pressurize that thing maybe to, I don't know, 150 psi. Like, man, hope that thing doesn't like leak. Oh my goodness. All right, Alex asks, what kind of safety measures are installed so they don't blow up the whole block? I don't know, man. I don't work for OSHA. I don't know. I imagine some sort of secondary containment. If you've watched Chernobyl on HBO, whatever they didn't do is probably in order. Okay. Right. So that gives you an idea of like how big these autoclaves can be, especially for these huge materials. Yeah, pressure relief valves probably a good option. Okay, so that's autoclaving. Useful for making the most expensive but best materials. Next, the filament wind. All right, so filament winding is most useful when you're going to make like cylindrical structures. And I kind of showed this when I first introduced wet processing. And it's like the opposite of a lathe. All right, so if traditionally when you think of like a lathe subtracting material on like a rotating mandrel, this would be the opposite of that. You have carbon fibers that are being wet by passing them through some resin bath, and then you're applying them to some mandrel as the mandrel like rolls around and the arm like applies it in sort of this like robotic fashion. So this is really good for making cylindrical parts. Cylindrical pressure vessels are very commonly made using this apparatus. Rocket casings, missile casings, baseball bats, etc., would be made using this particular methodology. Some hockey sticks are made this way. Lacrosse sticks are made this way, a lot of them. So there you go for filament winding. And the fabric doesn't necessarily have to be wet for this process. You could actually like wrap dry fabric around a mandrel and then sometime later infuse that fabric into infuse the resin into the dry fabric later, right? This is typically a precursor to vacuum bagging if it's dry fabric that you're applying. And even if it's wet fabric, usually it's like a vacuum bagging process. Here are a couple of examples. On the left here, you see some carbon fibers coming off of what would be some mandrels and some spools over here to the left. And it's just being wound around this, looks like an aluminum mandrel here. And it's kind of being wound in just a 0-degree orientation. And this just shows you dry carbon fiber being woven around using this filament winding process. Here's an example of wet filament winding, where actually these glass fiber strands are kind of passing through a resin bath. You sort of see the resin bath right here. It's getting like dipped into like a layer of epoxy right here, and then coming through some metering rollers here, and then being woven or directly applied to the mandrel and being spun around. I imagine for a mandrel of this size, the epoxy that's in this particular filament winding process has like a very, very long shelf life. All right, we're talking probably or like working time, gel time, like maybe 8 hours of working time or something along those lines. Right? So you got to wrap that whole mandrel before it like gets solidified. You know, got to have a long working time. All right, some of the advantages and disadvantages. So filament winding is great for making these cylindrical structures, like I said, or nearly cylindrical structures. So kind of on the upper right hand side of this particular slide, you see a couple of shapes that might be able to be made using the filament winding procedure. You basically have to have like um, convex cross sections. Okay, so any convex cross section you can more or less make using this procedure, right? So something that looks like this. Hockey sticks, might look something like this. Lacrosse sticks looking something like this. Ovals, half circles, all that stuff is sort of fine. The disadvantage is you can't really make non-cylindrical components all that well. You got a lot of capital costs here when you're talking about purchasing like an inverse lathe to make this happen. Time consuming. It can take a while to sort of wrap all this around, and it's sometimes difficult to release from the mold. So if you think about like wrapping all of this fabric around a mold, you're probably wrapping it like pretty tightly so that it stays on there. Then if you have the cure process, the composite wants to tend to shrink around that mold. And so it can be really, really hard sometimes to actually get that um, woven fabric that's actually been solidified after the manufacturing process. It can be really hard to sometimes get that off the mandrel. So a couple of ways that they typically will do this, and I see I have this question in the chat. How do they intend to get the cylinder off? It's the question in the chat. Well, they hire Arnold Schwarzenegger, and he comes. No, I'm just kidding. Usually they'll have what are called collapsible molds, right? So the mold itself will be able to be collapsed. So maybe the mold is internally pressurized during the process, and then you take the pressure off. Think of like a bladder system, all right? Like maybe my mold is pressurized, and then when I'm done, I can take the pressure out, and my mold collapses, and I can sort of work with my part that way. You might consider using a light foam mold, and then afterwards you just sacrifice the mold and say, well, I'm just gonna, machine off the mold and away I go, right? Cool the mandrel, asks Andrew. Yes, sometimes that's used, but that's not all that common. Sometimes, but not as common. Okay, so there's your filament winding. Anti-lathing. The anti-lathe. Next, pultrusion. Pultrusion is a process for making very long continuous cross-section pieces. So think of like, making long I-beams of steel. That process is very similar. You just have like a bunch of steel kind of going through a mold, and it comes out, and it's like this long process that just makes like a continuous I-beam of steel. The same idea kind of holds here. You sort of start on the left-hand side of this particular image with all of the, carbon fibers and et cetera, et cetera. Those are coming in here to a resin bath, which you see here that kind of wets out the individual fibers. That passes into a heated die, a heated sort of a mold, and that die has a particular shape that the cross section will also have when this whole process is done. So that die can have like an I-beam cross section, it could have like a C-shaped cross section. All sorts of crazy cross sections are possible. You just kind of have to manufacture and make the die appropriately. Then there's some puller that's pulling all of this through the die. Usually it's called a cat track. Usually that's pulling everything through. There's a cutoff saw to give you your materials of the appropriate length, and then you just have this continuous process making these continuous materials. Okay. I want to talk about the cure process itself as the material goes through the die. So this is kind of an interesting example. This is taken from one of the books for this course. The idea here is that from left to right, in this graph, we're sort of tracking along the fibers as they move through the die in the pultrusion process. And we're looking at a couple of things here. First is the die temperature. So the die temperature is sort of increasing along the length of the die and is maximum at the outlet. And we can look at sort of how the viscosity of the resin sort of, evolves during this process, and also how the fiber and resin temperature will go. So here's the fiber resin temperature coming in, and it's going to hit this heated die, and obviously that fiber and the resin is going to start heating up, heating up, heating up. And because of the exothermic process that this resin goes through, it's actually going to heat up past the temperature of the mold itself. So at some point, like, this reaction is going to have a temperature that's higher than the die itself. It'll eventually come back down to reality. Oops, there goes gravity, and cool as we make our way through. But the idea is that because it's this thermosetting reaction, your viscosity is initially going to lower because you're increasing the temperature, and then as the reaction proceeds, the viscosity is going to shoot up to infinities because you're making your hardened part. So this is a typical evolution of how pultrusion might work in a die for like a continuous process. We're at like or like stable conditions, equilibrium conditions, right? Okay, so that's kind of a cool little figure there. Thought it'd be nice to show. And here's an example of the process in production. So this kind of goes from lower left in this clockwise sort of fashion here. So this is an example of a pultrusion process where a bunch of fibers are being fed, and then there's like liquid resin beyond like what looks like this green crossbar here that's getting applied to the resin. All the fibers are now coming into sort of this staged alignment where they're getting fed in a little bit at a time and compacted and contracted into what will eventually be like the die shape coming up later on down the line. Then they're all fed in here into the die, and you see like some of the extra resin that might not have gotten appropriately metered before it came here is now being metered by the die. So a lot of the extra like epoxy is just sort of like dripping off here. It looks kind of nasty. But it's going to come into this die, and this die is heated. And on the back end, you're going to end up with a very nice looking cross section here. This is the cross section of an aircraft wing. Looks like some sort of wing element here, maybe for UAV or Formula vehicle spoiler or something. Who knows? I don't know. Only the people that did this know. Right? So there's an example of the pultrusion process, making these continuous cross sections. Very useful for I-beams, wing elements, whatever, etc., etc. All right. Some of the advantages and disadvantages: you can make these continuous cross sections of quote unquote infinite length. High volume production, right? So if you have enough fiber and you can pull your fibers fast enough, you can make like quite a bit of material here. It's like a continuous process, right? So if you just run this 24 hours a day, you're going to have I-beams for days, all right? Concave cross sections are possible. Unlike the filament winding, you could make sort of that like star-shaped pattern if you wanted. All right. Disadvantages, though, sometimes it can be pretty difficult to achieve high fiber volume fractions in this particular situation, and that's just because of how the fibers are coming in. It can sometimes be difficult to align it around, let's say, like sharp edges of the cross section and so on. So sometimes it can be hard to achieve these high volume fractions. Tooling is very expensive, so you got to buy this pultrusion machine. All right, you got like the cat track that's expensive. This whole production line is like $1 million probably if you're talking about like producing this from the ground up. All right, tooling costs expensive. Die mold required for each cross section that you use. Really only useful for thermosets. I have seen some thermoplastic pultrusion in my life, but only like lab scale and very like experimental ideas. Typically, thermosets is really your only pathway here. Okay. Finally, I think this is the last one we talk about, is reinforced reaction injection molding. So we talked about sort of like the reaction injection molding as the dry process, where you put all of your fabric into your mold, and then you inject the two-part resin into the closed mold. That all cures, you release your part, you're hunky-dory, you're good to go. There's another way that this can be done, and that's called reinforced reaction injection molding. And this is typically done with like short fibers or particulate reinforcement, where you have the particulates or you have the short fiber in one of the two resin components, and that gets mixed together with, like, let's say the hardener, and that's all injected as one. So you're actually injecting the reinforcement alongside the resin into the closed mold. So the problems here Well, let's talk about what this is useful for. Usually thin parts, high volume parts, okay? Reaction injection molding, almost always thin, high volume production parts, all right? So think like a car hood would be a good common example, all right? Very thin, repeatable structures, high volume, that would be something that you would see. The problem is that you really are limited on the volume fraction that you can achieve. And that's because you've got like this short fiber reinforcement that is sort of like mixed in with the resin. And if you're talking about an injection process where you have already sort of a moderate viscosity like resin, and then you're adding a bunch of particulates to that, like the resin, like the viscosity of that resin and fiber mixture is going to be like astronomically high. And so the pressure required to actually push the fiber reinforced like liquid resin into the mold is like super high. All right. So really the maximum fiber volume fraction that you can get with this like reaction injection molding is somewhere in the neighborhood of about 25%. And that's like the absolute upper limit. I would say most processes are like 10 to 15%, and even 15% I feel like is rather high. Okay. Now, one last thing I want to make mention about is some of the problems aside from things I've already mentioned about manufacturing. And one thing I talked about when we first introduced this lecture was this idea of degassing the epoxy. Now, if I mix part A and I mix part B together with my epoxy, and I'm going to use that for a manufacturing process, whatever that process is going to be, if I mix all that up, I'm like inducing bubbles in that by mixing it. Okay, so think about like this liquid resin here, mix, 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 mix. Okay, it's got a bunch of bubbles in it now. So if I don't degas that resin, by degassing I mean like take that cup of resin, put it in an oven and pull vacuum on it. So think like defizzing your soda. All right, if I don't get all those bubbles out and I use that sort of gassy resin in my production, I'm going to end up with composites that have holes in them. All right. And that's because like the bubbles that are in the resin, the liquid resin, when you inject it, once that solidifies, those bubbles are still like going to be there. And you're just going to end up with like holes in your epoxy. That's, not so great. All right. You guys talked about stress concentrations from hollow inclusions and parts in your 2004 class, I hope. Did you guys talk about stress concentration? 2004? Yeah. Okay. So stress concentrations from voids, yikes. All right. And you can sort of see that in these cross sections here. So these big black circles here, these are voids that are inside of the structure. And those came either from like moisture that was included in that piece that, once the moisture goes above 100 C, it's going to turn to steam, which is basically the same idea. Um, or maybe the resin itself had like some gassiness to it. It wasn't properly degassed. Okay. So when you first mix, these cups are going to be placed into a vacuum oven to degas. And the process that you're going to use requires more or less degassing. If you're going to use the resin in a positive pressure application, which is like resin transfer molding, because you're pushing the resin through the mold, you don't need as much degassing time as if you're going to have some vacuum process, right? And that's because the vacuum process will just, by its standard physics, will want to try to expand those voids. And so when you're going through a vacuum process like Vardum, vacuum bagging, autoclaving, etc., you'll need quite a bit of degassing time to make this happen. So if you're ever manufacturing composites and you don't degas your resin, you're going to end up with you're going to be in a pretty tough spot, right? These voids reduce strength severely, and these graphs are meant to sort of depict the levels of reduction of properties that you might have if you have voids included in your piece. So let's take a look at, for instance, this graph here in the lower left. We have on the x-axis void percentage in your composite, and on what would be this y-axis here, this is the flexural sort of strength of this piece that it could handle before it failed. So if we don't have any voids in our piece, 0% voidage or generally low voidage, I would say that the strength of this particular material is about 120 MPa, all right? But if we include even like 6% voids, we're already down to like 80% or 80 MPa, which is maybe like 75% of the strength. So even including just like 5-6% void content inside of your composite can limit your strength by 25%, just like an enormous amount, right? So take that to heart. And here we are at like 20% voids, which your composite was like horrible. I mean, it'd be terrible looking. This is just like right to the trash, like right to the garbage with you. All right. Okay. Similar looking graph here with interlaminar shear strength as the metric instead of tensile strength or flexural strength. So again, this is even more severe. So if you have void contents of 4, 5, 6%, you're going from interlaminar shear of 16 to 18 down to 8. So you've cut in half basically your interlaminar shear strength by including 5% voids. So moral of the story: voids not good. You should avoid them. Okay. I'm hoping there's some people chuckling there. I don't know. We gotta do something here. All right. So, in conclusion, for the composite manufacturing portion of the course, and this generally will conclude sort of like the materials portion of the course, is that there are a lot of different manufacturing types for composites. I didn't even really cover all of them. I covered what I think are like the most important ones. And there's advantages and disadvantages of each type. And so you really have to consider like, what's the volume of production? What is this going to be used for in the end? Is it structural or non-structural? Um, how repeatable is the process? All right, Vardum is not as repeatable as like injection molding. All right, so all these sorts of things you have to really consider if you're going to use these things in production. All right, so other methods we didn't talk about include spray up molding, compound manufacture. This is like a whole other. I mean, you could have a whole lecture on that alone. Press forming, thermal forming, free forming, other sorts of methods that are out there, but not as common. Okay, I'm really only going to focus on the big ones. That's RTM, Vardum, vacuum bagging and autoclaving, Pultrusion, filament winding. Those are like, you know, 90 to 95% of the production of composites in the world. All right. Any questions about the manufacturing portion of this course? I've also included a reference here for materials if you guys are ever going to make these. So if you rob a bank and you have enough money to start making composites, here you go. Here's your list of manufacturers that you might want to revisit at a later time. Or if you become a professor at a major university and they're willing to fund you making crazy composites, here's your list of manufacturers. All right. Any questions? Xavier says, materials portion already done? Yes, sadly. I know. Sad panda. Good old McMaster car, says Justin. Anybody ordered anything from McMaster in the past? Raise your hand. Yeah, okay. McMaster's like the... You want to pay 3 times more for something to have it tomorrow? Go to McMaster. All right, Kev, you have your hand raised? Oh, those are you guys raising your hand for McMaster. Got it. McMaster is the best company ever. And you want to pay 3 times the cost and get it tomorrow. Onwards, I say. So that sort of concludes the materials portion. Now we're going to start in on the mechanics portion. All right? And here fourth, hence to fourth, I will be using the writing pad to sort of work my way through lecture. I have the slides posted on Blackboard, and you can sort of follow along with the slides that are on Blackboard if you'd like. I'm going to sort of mimic pretty closely my lecture notes that are posted on Blackboard, and I posted these today. And the topic that we're going to talk about first is, and generally the way that we're going to approach this course is we're going to start from like the smallest metric possible and work our way up to structures. Okay, so the first thing that we're going to talk about is micromechanics. All right, now let's just like think about this word for a hot second. Mechanics is, the thing that you've studied for the last 2-3 years, etc. Mechanics being mechanics of materials in this sense, which is sort of like the stress interactions that exist in these composite materials. Okay. Micro being the smallest sort of element we might want to think of for considering some model useful for predicting properties of composites. So when you think micromechanics, you probably want to think of like a small model representative of a larger piece. All right, so this micromechanics models, these are small models representative of larger pieces. Spelling is hard. I before E except after C and something something I don't remember. So the very first model that we're going to talk about, and the most basic model, is what you would just think of as a single fiber in matrix. And the model that you might want to think about in your head is here's your fiber, and here's your matrix. Okay? If I pull on that in this direction, if I pull on that into and out of the plane, how does this one little interactive piece respond? Then if I thought about replicating this little model over and over and over and over and over and over and over, that would be representative of like a full composite. That's the general idea. Okay? So that's kind of the foundation for what we're going to do over the next week to week and a half with these particular models. All right? So away we go. Little introduction to micromechanical models. All right. Now, like I said, can sort of be analyzed on many scales, and we choose to start at the smallest level. Okay. And so we're going to start with simple interaction between a single fiber and surrounding matrix. Putting into words what I already said. So these are kind of known as micromechanical models. All right. I've got some pictures on the slides, and I think I'm going to bring them in here just to kind of like show you what I might mean. So if you thought about like a unidirectional carbon fiber reinforced plastic cross section, it's made up of like all of these individual fibers here. Maybe black's not my best color. Maybe red. So these individual single fibers that you sort of all like, you see all these individual fibers here coming out at you, all these little circles that are coming out at you, right? And so the model that you might want to think of looks something like this. Single fibers surrounded by an appropriate amount of matrix. So what we're more or less going to do is we're going to look at one of these little individual elements, do the analysis of that one particular guy, and then basically multiply that up to get what looks like a model like this. So here's like a macro model of many of these smaller like micro pieces. All right. So this would be your macro model. And then if you had like a sort of like the smallest element, which is sort of what we're going to do, it would look something like this. So here's your more or less your single fiber model. You have this big surrounding composite, which is just like quote unquote the rest of the stuff. All right. And then here's your matrix material, and here's your fiber material. All right. So there's your rest of the composite. It's the rest of the story. So let's talk about the models we'll cover, because there are a variety of different micromechanical models that we're going to evaluate. All right. The first and the most basic, we just call the mechanics of materials model. The next is the semi-empirical. I gotta spell this right. Empirical model. It's most often called the Halpensei, named after two guys, Halpen and Sei. The Halpensei model, named after Mr. Model, exactly. Both of these models here are for continuous fiber composites. Right? So we have kind of like two models, and they're somewhat related actually, for continuous fiber composites. And we'll also look at some models for non-continuous fiber composites, specifically short fiber models. And we'll also look at particulate models. All right. Before we move on, with micromechanical models, the fiber direction, sort of by nomenclature or by standard, is always the one direction. And by one direction, I mean a coordinate in a 1, 2, 3 coordinate system, not the boy band. Okay? Don't get confused when I say one direction. I'm not talking about, singing group. What do they even like? I don't even know the songs they sing. I'm sure I heard them on the radio, but I just like don't know. Anyone know One Direction? Come on, I know you want to sing it. You're looking at it. Yeah. She's embarrassed. We'll get the karaoke up here. I'll put it up. You can just go to town. Okay. All right. It's always the one direction. So what do I mean by that? If we look at our the model that I had originally, which was like some matrix material with some fiber. So here's the fiber matrix. Well, this is like the 2-3 plane. All right, because the one direction is along the length of the fiber, which we'd assume is into the plane infinitely. Right? So maybe if you're looking at this from the side, then you've got something like this, where this is like a carbon fiber singular that's embedded in the epoxy matrix. This is like the side view. And maybe this is like your 1, 2 here. All right, so that's just by standard nomenclature, the fiber is always in the one direction for these micromechanical models. All right, I just got to get that out of the way so that we're clear when I start talking about one direction. But which one direction? Maybe I'll play that like as my lecture lobby waiting music next time. It's like very appropriate composite music. The One Direction. God. Okay. Let's move on. And let's talk about an important concept. I've talked about this a couple of times already, but let's put it in writing now. And that is the fiber volume fraction. So let's put some definitions to the words, eh? I think the definition is pretty self-explanatory. It's anyone want to guess? How about the volume fraction of fibers in the composite? Mathematically speaking, we might want to be, distinguish this mathematically. We're all engineers. We speak math. Okay. Well, most of us. We'll typically write this as V sub F, volume fraction, is equal to, and I'll be I have to distinguish in this class the difference between volume fraction and volume, okay? Because there are different things in this class. The amount of volume of fibers is a certain number in like meters cubed, okay? The volume fraction of fibers is some percentage of fibers inside of the composite as a whole on a scale of 0 to 1. So in order to distinguish volume fraction and volume in this class, I'm going to strike through the V when I talk about volume. So this is volume of fibers over volume of the composite. All right, so let's define all of these things. Let's talk about volume fraction of the matrix. Is a similar idea. You'll have volume fraction of the matrix is the volume of the matrix divided by the volume of the composite. Right? That's how you would measure that thing in the lab. So let's define all of
What does that say?
What does what say?
It starts with an S. S-I-M.
Similarly.
What does that whole sentence say?
Similarly for matrix volume fraction. Yeah, handwriting bad. Let's do it. Let's redo it. I have someone in my ear yelling at me for handwriting. Similarly, for matrix volume fraction. Is that better? Where, and we'll define each one of these things. VF is fiber volume fraction. And this is going to be on a scale of 0 to 1, right? 0 meaning I don't have any fibers in my composites. 1 meaning it is entirely fibrous. Right? Capital VF is the total volume of fibers in the composite. Right? And that's going to be some volumetric number in, let's say, meters cubed or something along those lines. Right? You can similarly have Vm, which is volume fraction of matrix phase. Again, this is on 0 to 1, a scale of 0 to 1, 0 to 100% if you want to think about it that way. V strike through is the volume, total volume of the matrix. Again, this would be in like meters cubed. And then your VC is total volume of composite. Okay, and we have to be very clear here in that we've made the assumption that there's no voids in your composite. Now, if we make the assumption that there are no voids, then there are some additional sort of constitutive relationships that we just generally have here. So if we assume no voids, then obviously the volume of the composite is the volume of the matrix plus the volume of the fibers. All right, I think that's pretty straightforward and obvious. Right? So if we divide all of this by the volume of the composite, you're going to end up with an expression that looks like 1 is equal to volume fraction of the fibers plus, sorry, let's do the matrix. Volume fraction of the matrix plus volume fraction of the fibers. Right? Or if you rearrange, the volume fraction of the fibers is simply 1 minus the matrix volume fraction. Sort of makes sense. So if your composite is a 100% whole, then whatever portion is not the matrix is the fiber, and vice versa. Okay, I think that's pretty straightforward. All right. And also, if we're given our sort of singular fiber model, okay, and we're going to extend that to a bunch of fibers that are aligned in a row that make up our composite, we'll say that if we're given a composite cross-section, and that cross-section only contains unidirectional fibers. In the one direction. Okay. Then you may estimate the volume fraction of fibers from aerial measurements. All right, what do I mean by that? All right, example cross-section. This will be the last thing that we do today. I know I'm okay. I'll leave this here so you can keep copying, and I'll actually pull from over here. So if you've got a cross-section that looks like this, all of your fibers are moving in the same direction, and this would be what we would consider a unidirectional composite because all the fibers are moving in just generally one direction. Okay? If that is the case, then you can sort of infer that they all have the same length into the page. Let's call that length script L. Right. So we'll say the fibers have a length of LF. This is also equal to the length of the matrix material into the page, also equal to the length of the composite into the page. Yes, this all sort of makes sense. We would assume that it's continuous and all of the same length into the page. If that's the case, then your fiber volume fraction, which we said before was like the volume of the fiber divided by the total volume of the composite, is going to equal something like the length of the fiber into the page multiplied by the area of fibers that you see in this cross-section, divided by the length of the composite divided by the area of the composite you see in this cross-section, where if these two lengths we know are the same value, then you could say that you can measure the volume fraction of the fibers by looking at a two-dimensional cross-section and simply dividing by the total area of the fibers that you see in the cross-section by the area of the composite. So if we looked at this image and we measured the total area of all of these individual fibers, assumed that they're all the same length into the page as the black matrix that exists there, we could determine what the volume fraction is of this whole composite and say that, I don't know, if I was looking at that, maybe 70%. All right, 70% volume fraction approximately for that image, so it's nice to look at. That's it for today. I kept you maybe 1 minute late. Apologies for that. See you guys on Monday. We missed Zane. I'm bringing a mic on Tuesday or Monday, whatever it is. Yeah, it's Ethan. It's area. I know. I was rushing a little bit at the end. Apologies. See you later, Mr. Rogers. I have an answer. Jail time.